Good afternoon, dear students. Today we will learn uniform convergence of a set of functions. In our previous lecture, we already learned about the point-wise convergence of a set of the functions. Uniform convergence is a type of convergence of a sequence of real valued function. We know about the real valued function. That is a function like f and x, in which the n is always greater than equal to 1 and the set of natural number and x is independent variable. And f and x, x and all the f and x tends to r and n from 1 to infinity requires that the difference, this is very important line, requiring that the difference to the limiting function. Okay, first we need a limiting function for understanding the uniform convergence and for finding the uniform convergence of a set of the set of the functions, requiring that the difference to the limiting function can be estimated uniformly on x, and that is the independent of x belongs to x. Okay, uniform convergence property implies that the limiting function f has some important properties. Always the limiting function is continuous. If limiting function is not continuous, the the set of the functions is not uniform convergence, and the limiting function is always boundedness, and the limiting function is satisfy the Riemann integrability. Okay, these are some important property of the limiting function. And for example, the concept about the limiting function and the uniform convergence, we can understand it with an help of example. Let us take an example. Suppose that we have a function f and x equal to x to the power n, and the domain between 0 to 1. Okay, and n is always x belongs to 0 to 1, x belongs to 0 to 1, and n belongs to the set of natural number. Okay, in this case we have, when we approach n from 1 to infinity, then f1 x equal to x, this is first function. F2 x equal to x square, second function. F3 x equal to x cube. Similarly, we have f100 x equal to x to the power 100, and similarly we can write f f infinite x equal to x to the power infinite. Okay, and fn or nth term is the last term, for example fn x equal to x to the power n. If you want to find the limiting function of this type function, then we can understand this concept with the help of a graph. Suppose that this point is 0 and this is 1, this point is 1. Okay, for first function f1x, the graph of f1x is always when x equal to 0, then this is 0. When x equal to 1, then this is 1. It means the graph of this is, suppose that this point is 1 in y-axis, then the graph of this function is this. Okay, it means this is the graph of f1x. Okay, similarly f2x, x square, when we approach x from 1 to infinity, when we approach x from 1 to infinity, when we put x equal to 1, x equal to 2, x equal to 3 and so on, then this is the graph of a straight line passing through the origin. And in case of second function f2x equal to x square, suppose that x equal to 0, then this is 0. When x equal to 1, because the interval is 0 to 1, x equal to 1, then it is equal to 1. But when we take the a point in the middle of this interval, 1 upon 2, when this is 1 upon 2, then when x equal to 1 upon 2, then this is 1 upon 4. It means this point is 1 upon 2 in y-axis and 1 upon 4. It means this point is this. Okay, The graph of this function is like this. Similarly, f3x equal to x cube. Okay, when you put x equal to 0, then this is 0. When you put x equal to 1, then this is 1. It means the initial and the terminal point of this function is same like the above two function. But when you put x equal to 1 upon 2, then it is 1 upon 8. It means this is like passes through this point. Similarly, when it is 1 upon 4, then this for another function, this is the function f2x. Similarly, this is the function f3x. Similarly, this function is f4x. Okay, and similarly, if you put f100x, okay, f100x, x to the power 100, when you put x equal to 0, then this is 0. Okay, when you put x equal to 1 upon 2, then it is equal to 1 upon 2 to the power 100. 1 upon 2 to the power 100. 1 upon 2 to the power 100, it means 0.0000, etc. Because when we approach toward 1, okay, then it is equal to 1, but between the 1 and 0, the limiting function tends to 0. Okay, the limiting function tends to 0. When you approach to 0, then this is limiting function tends to 0. It means the limiting function of these all the function tends to the line 0. Okay, the limiting function for all these function is equal to 0, but the limiting function for this line is equal to 1. Okay, it means we can write the limiting function of this function fx equal to 0 and 1. Okay, the limiting function is fx equal to 0 and 1. 1 in the case when x equal to 1, then this is the limiting function is 1. And when x equal to for this function, okay, when x belongs to 0 to 1, this is closed one side and open one side. When you approaching to 1, then this is always 0, because for all these functions the limiting function is 0, and for this function the limiting function is 1. Clear? It's mean the limiting function has two values, one is 0, other is 1. The limiting function is discontinuous. This function is continuous. Every function of the fnx, because fnx is a set of function, and every function of fnx is continuous. All are continuous. Okay, but the limiting function is discontinuous, because when we are approaching to 1, then in the neighborhood of 1, the limiting function is 0, but at 1 the limiting function is 1. This is discontinuous. If the function is discontinuous, the limiting function of this function is discontinuous, then this function is not a uniform continuous function. This function is not a uniform continuous function, because the limiting function is discontinuous. Discontinuous limiting function, limit function. Okay, one is the discontinuous limit function. All the functions are continuous, but the limiting function is discontinuous. And the second concept is all the function from f1 to f infinite has a limit point, has a limit. It's mean the function is a pointwise convergence, but the limiting function is discontinuous. So the conclusion and the answer of this question is the function is not uniformly convergent, but it is pointwise convergent because the limiting function is discontinuous. Okay, this is the answer of this type question, and this is the concept behind the uniform convergence. And the uniform convergence always depend on the limiting function of a set of function. Okay, so in next lecture we will solve another example of the uniform convergence. Okay, students, thank you.